Good morning, Sandra.
Good morning. Thank you for joining us.
Sure.
So after small break, we are back, and now it's time for your presentation. Let me introduce Pavel Yosifovich from USA, and now it's yours. Thank you.
Yeah. Should I start right now?
Sure, you can.
All right. So let's see how do I share my screen. So good morning. I think we should start around 12 p.m. Right? But yeah, I'm happy to be here. My camera is not really aligned in a good angle or something because my setup is a bit weird. But we'll see what we can do. So let me first try to share a particular screen. Okay, let's see. Okay, can you see my shared screen?
Not yet. On the way, I guess.
See, okay.
Yeah.
How about now? Yeah.
Now we see.
All right. So yeah, I guess I'll start. So welcome everyone. Thank you for joining me, whoever is live today. I want to talk today about something called ntdll or Native API, which is the fundamental Windows API, so to speak, that we can use to access the kernel. And so I call this session the native powers because we're using the native API. And of course, I'll explain what that is. So my name is Pavel. I've been around in the security space and the programming space for many years now. You can see here some of my books. Please buy them. They make me money, so it's always a good idea to buy them. And what I want to point out here is just a couple of things. So first, I'm a founder at the TrainSec. With TrainSec, you can find lots of articles and blogs and videos related to Windows internals and security and cybersecurity and malware analysis, things like that. And also there's like courses there you can purchase, but many things there are free. And also there's my YouTube channel. You can see the link at the bottom, which has lots of videos related to Windows internals and low-level programming. So again, this is mostly free, so just go ahead and register or subscribe and you can watch that. So without further ado, let's just get into that. So we'll start with the basics of Windows architecture and exactly what is a native API, what can we do with that. I'll talk about native applications, some of the capabilities of the native API. So when you look at applications on Windows, if I run something, say, like Explorer or a Notepad or anything like that, what is actually happening there? So originally, Windows NT back in 1993 was the first version of Windows as we know it today. It offered actually three types of applications. The first one is what we are familiar with today, which is the Windows application. And these are the normal applications we're familiar with. But in fact, there was also two other types of applications that were available at the time. They were based on POSIX, which is a certain standard of Unix, and OS2. And the idea was that Microsoft didn't really know whether Windows NT is going to succeed. And so they decided to cover all their bases and allow developers from, say, the Unix world and from OS2, which was popular at the time, to recompile their applications using a Microsoft compiler, get a portable executable API, and then run it on Windows, and it will just run. And that actually worked. So it did work, but at the same time, Microsoft didn't really know whether NT would succeed, and it succeeded way beyond their expectations. So with time, they decided to remove some of these subsystems. In fact, POSIX and OS2 were removed eventually. And so each one of these subsystems had its own DLLs it would link against. That would be the APIs of those subsystems. So if you're familiar with the Unix, for example, or Linux, which is from that perspective the same thing, use APIs like open or read or write. These kinds of things were supported. And the question is, how would that actually work? I mean, how did that work on a Windows system, which is not a Unix system. And I'll explain that in the next few slides. And the basic idea was that they had their own DLLs, their own implementation of the API, but they all called the common API, which is the native API, which I'm really want to talk about in this session. And every subsystem also had a process that managed all the other processes of that subsystem in certain ways that makes it more appropriate for the behavior expected by processes in that subsystem. For example, for POSIX, which is basically Unix, there's these signals thing. So someone has to manage these things and like work with them. And there was a subsystem process manager. In the POSIX world, it was called psx.ss.exe back in the day. Now, the term subsystem is a bit misleading or perhaps a bit overloaded these days, because many of you are probably familiar with the idea of a Windows subsystem for Linux, which also has the term subsystem stuck there. So is that the same thing? Not at all. It's actually implemented very differently. And if I have time, I'll talk about that a little bit. So what do we have today in terms of subsystems? We have just the Windows subsystem that remained. OS/2 was dropped in Windows XP simply because nobody was using it. And POSIX support was also dropped in Windows 8.1. Again, no one was using it enough for Microsoft to like invest time maintaining that. If you have a Windows 7 machine lying around, maybe a virtual machine, you can still find POSIX there. You can run POSIX applications. For example, you could do something very interesting, such as creating a file. In fact, you can create two files that have the same name, but different case in the same directory. Because Unix and Linux are case sensitive in terms of file systems, but Windows normally is not. If you try to do that with something like Notepad or Explorer, you'll find it doesn't work. If you try to do that with POSIX, it does work. And it just shows you that certain aspects of the kernel are not necessarily exposed to everyone. It means that NTFS as a file system is in fact case sensitive. It has really no issues with case. However, the Windows subsystem just asks the NTFS file system driver to be case blind, to disregard case. So essentially today we only have one true subsystem, which is the Windows subsystem. So we're running everything like Explorer, Notepad, Visual Studio, Edge, Chrome, whatever. These are all Windows subsystem applications. And these have nothing to do with the Windows subsystem of Linux, for Linux, which is something that Windows supports today, WSL. And the reason is that there's no need for any recompilation in WSL. With WSL, you take an existing binary from Linux and just run it on Windows. You don't have to recompile. You don't have to do anything. You don't need to have the source code, in fact. So it works in a very different way, which maybe I'll cover briefly at the end if we have time. So let's summarize that by looking at the Windows architecture and see how these things kind of converge. So if you think about processes, we have these processes like Explorer running or Edge or any other process you like. And processes have to do stuff. They want to do stuff. They want to open files. They want to allocate memory. They want to load DLLs. And for that, they're going to need to use certain APIs. And these APIs, as part of the Windows subsystem, DLLs are contained within a bunch of DLLs like kernel-32, GDI32, user32, and so on. And so, for example, if Notepad wants to open a file, which is something we typically do with Notepad, those that are using Notepad, we're going to go to the File Open menu, and Notepad is going to call the Create File API, which is the official documented Windows API for opening or creating files. And this is implemented in kernel-32.dll with but by the way, despite the name, it's still in user mode and it's 64-bit. If the process 64-bit, the name is kind of historical. In any case, since this is also happening in user mode, you can't really do that. You can't really open a file because at the end of the day, a file can only be opened by the kernel, by the NTFS file system driver or another appropriate driver. So we somehow have to go into the kernel. So create file can do certain things like check parameters, things like that, but at the end of the day, it has to move things forward, and it's going to invoke a function which is part of the native API implemented in ntdll. This is the common infrastructure of all the Windows APIs, basically, or the fundamental Windows APIs. This is the thing that was common to other subsystems as well. So in the POSIX subsystem, for example, if I call the open function, which is a Unix or Linux API, it will call the ntdll as well, and the function there is called ntCreateFile. So createFile in the Windows subsystem calls ntCreateFile, and open calls ntCreateFile as well. So ntCreateFile is something more fundamental that is common to any subsystem that sits in Windows. And that's really how things work. So ntdll is going to have its ntCreateFile function there, and it's going to be called. But this is not the end of the story, because what would ntCreateFile actually do? ntCreateFile is still in user mode, which means it can't really open or create a file regardless. So what it's going to do is going to make the transition into the kernel using something called a system call. Because really, the kernel is the only one that can do all these low-level things. It's just a matter of asking the kernel. So you can't just call some arbitrary kernel function because you feel like it. That would be a big security breach. Instead, you can only go through official channels. So these native APIs like ntCreateFile are the official channels. And so ntCreateFile is going to make the transition into the kernel by using a machine instruction like syscall It's going to put a number which represents the system call that we want to invoke right now in a register. In this case, it's the EAX register. So for ntCreateFile, there's one number. For ntReadFile, there's a different number, and so on. So every system call has its own number. And then it's going to make that transition into the kernel, where there's a central function called the system service dispatcher, whose purpose is to take that EAX, that system service number, and index that into a table, which is called the system service dispatch table, which many of you probably have heard of, which has all the entries for all the native functions, all the system calls, and then just invoke the system call, which is going to call the appropriate part of the kernel, and then call the appropriate driver. I'm not kind of drawing that in this diagram to simplify things a little bit, but I'll show that in the next couple of slides. And then the operation is going to happen, may succeed, may fail, depending on the call itself, and then result is going to go back into user mode and back to the original caller. So that's how any Windows API really works. And it doesn't matter if you're using C or C++ or some other high-level abstraction. For example, if you're using, say, C# or Java or Python or Rust, it doesn't really matter. Any function that you call there that does something based on I/O, like trying to open a file, it's going to eventually call createFile or ntCreateFile directly even. It's possible, but you have to go through ntCreateFile. You can't just do that in any different ways. Just not possible. That's the way to ask the kernel, please open a file or please create a file, which again may or may not work depending on the caller, security, and things like that. In Windows, we also have services. So services are these processes that typically are managed by the service control manager. They can run automatically when Windows starts. We're familiar with services. Basically, services are normal processes, just have some special management on top of them. And they're just like any other process that can use the same subsystem DLLs just like anybody else. We have some system processes, those that typically are there. We typically don't touch them directly. They're kind of doing their thing, like the session manager and WinLogon and things like that. And again, they can use the subsystem DLLs, the normal Windows APIs, or they can work with ntdll directly. In fact, some of them have to do that, and these are called native applications, which I'll describe momentarily. And finally, I mentioned that there is a process that has to manage or provide some extra management over processes of that subsystem. So for the Windows subsystem, which of course is the only one that survived, it's called CSRSS, or the Client Server Runtime Subsystem. The name is, again, very historical, but there's one of those for every session in the system. What we want to focus here in this session is ntdll. What is going on in ntdll? How can we use that? What interesting aspects of ntdll are there? Because ntdll is mostly undocumented. And that's why it's so interesting, and it's also more powerful than the normal Windows API, which I'll demonstrate and discuss. So the first thing we need to talk about are native applications. Native applications are those that depend on nothing except ntdll. They can't depend on any subsystem. So if I mention that there's this just one subsystem, the Windows subsystem, we can say there's another kind of subsystem, which is not really a subsystem, but it's simply easier to think about it in this way. It's the native subsystem, or if you will, you can call that no subsystem at all, which means there is no subsystem DLLs, there are no Windows APIs being used or anything like that, the documented ones. Instead, there is a link directly to ntdll, and that's the only dependency. One example of native application is AutoCheck. You've probably seen the case where sometimes Windows doesn't shut down gracefully. The next time you start the system, you get this blue screen, and there's something that says that you want to check your disks. So what is that? This is in fact AutoCheck. And AutoCheck is one of those startup applications that are launched by SMSS, the session manager. The session manager is the first usable process created. It has a bunch of duties, and one of them is to launch all native applications that are registered in a particular location. And here's that location. There's a value called boot execute. You can find that in this location in the registry under HK local machine, system can control set control session manager. And the list of applications there, by default, it's only AutoCheck, but you can add your own if you wish. And then it will run automatically by SMSS at startup. And you can do very interesting things there, because when it's running with superpowers. SMSS has superpowers, and it's launching those applications, so they have superpowers as well. They can do anything they want, basically, on the system. So it's a very powerful thing. You can see this by looking at the registry, of course, but you can also use some tools, like in this case, you can use autoruns. Autoruns from CC internals, you're probably familiar with that tool, and if not, it's a nice tool to look at. Provides information about all the things that might happen automatically without you knowing necessarily that these things are happening. So there's the everything tab here, but there are some other tabs which provide a subset of that information. And one of them is boot execute. This is where we see everything that is running as a native, as a boot application. These are, we can see the list here of applications that are going to be run by SMSS. Like I said, by default, there's just one, which is called the AutoCheck. So it's, in fact, AutoCheck is just a name, but the command line is AutoCheck and star. Star just is a command line parameter to AutoCheck that says check all the disks, basically. But there are other command line arguments that AutoCheck can accept. And this is a native application. How can we see that? Well, we can, for example, go to something like a Total PE or any other application that can look at PEs. So if I take AutoCheck and just grab it from my other screen, doesn't matter, just get it from System32, you can see in the import it has a single dependency, which is really the one that matters, which is ntdll. That's the thing, it depends on BCD, is another helper library for accessing the boot configuration data, but it's not very interesting for our purposes here. So ntdll is the only thing. If you look at a normal application, something completely different, like more standard, say like Notepad, let me drag Notepad here, you'll see that in the imports, there's lots of things. There's GDI, there's U32, there are many of these API sets and common controls, lots of dependencies that are based on the Windows API, because Notepad is an application that belongs to the Windows subsystem. And you cannot run such an application very early in time when SMSS is the one launching applications. It can only use native applications that have just one dependency that matters, which is ntdll. So these are native applications. You can definitely write your own. And I'm explaining in the Windows Native API programming book that I wrote in 2024, I explain how to do that. It's not that difficult, but I can show you what that might look like. So I have an example here. So here's an example of a native application. What actually makes this a native application? The first thing is that if you note, there is no main function. There's no normal main function we're familiar with, because the normal main function that we're familiar with in normal applications. So here's another application which is kind of normal. So we have here a function called the main. Here's main that gets an argc and argv. So many people think that the main function is really the first thing that's happening in the process. This is far from being correct. In fact, if I put a breakpoint here, I'll see that, let me just run this just for fun. Doesn't matter what this application does. I just want to run this. So we get to a breakpoint here in main. So here we are. Here we go. We're in the breakpoint here. And if I look at the call stack, you'll notice that it's not really the first thing that is happening by far. It's being called by some invoke main function here. And this is being called by some scrt something here. And it starts with main crt startup, really. And so what we see here is that it's being called by something called the C runtime. So normally when we build applications, and if we look at any normal application, so to speak, you'll find that it's linking against the C runtime. And you might be wondering, why is that? Why do we link against the C runtime? What does that actually give us? So this gives us a few important things. For example, this main function, if you think about main functions in general, you've learned maybe officially, maybe you know that there is that main function, but the question is, who is going to call that? I mean, does the operating system really cares about this main function? The answer is no. It doesn't really care about this main function because this is just very specific to the C language or C++ language. So it doesn't really care about that, and someone else has to actually invoke that correctly. There's another thing. Suppose you're creating a global variable. Those of you that are familiar with C++, what happens if I create a global C++ object that has a constructor? We know the constructor has to run before the main function actually executes. Why? Because the C++ standard says so. So if the C++ standard says this is how it's supposed to behave, someone has to implement that behavior. And the question is, who is going to run those constructors? And the answer is the C runtime does that. The C runtime has that extra code that it's running that calls this constructor. So without the C runtime, we don't have that. It means that if you create C++ global objects and you expect the constructor to run in a native application, for example, where there is no dependency on the C runtime, it won't happen. So we kind of lucky or feel like it's nice to have the C runtime because it does a lot of things for us. So we get the behavior that is promised by the C and C++ standards. They promise that there's a main function, it's going to be called, you're going to get the parameters and all that. That's nice. So we get that by the C runtime. That's why we typically link with the C runtime. However, a native application only links with ntdll. It has no dependencies on the C runtime. It cannot, because the C runtime itself is built on top of the Windows API, which is not available for native applications. And that's why the example here for a native application, there is no main function. Even if I write a main function, doesn't matter, it's not going to be called. And in fact, the function name that is expected is called ntprocess startup. It's not going to be called main. I can actually change a linker setting and say, hey, let's call it main. I mean, fine. But it's not going to give us an argc and argv. It's not going to work out. It's expecting, in fact, it's giving us a pointer to the process environment block, or the PEB, which is something that many of you are familiar with probably. It's a user mode data structure representing some details about the process. It is mostly undocumented. And again, I describe many of its fields in the Windows Native API programming book and the course that I have on Transect. In any case, everything is there. In fact, the command line that we're familiar with argc and argv is there somewhere. It's just a matter of getting it out of there. And it doesn't have that nice argc, argv kind of split. We have to do these things ourselves manually. So that's the function. And in fact, if you go to the properties of this project, go to the properties in Visual Studio here, you can see that in the linker, in the input, we ignore all default libraries. We essentially don't link with anything except ntdll. And in the system, we can see the subsystem is native. The default that we'll see is something like console or Windows, representing one of these standard options that we use for normal applications. But we can't use that anymore if we want to write a native application that has no dependency on ntdll, except ntdll, and can run at startup by SMSS. So you need to change some settings here to make sure that there is no dependency on anything. So we get the PEB here, and then we can do basically whatever we want, but we can only use the native API. So for example, I'm using something simple here like ntdll execution, which is the equivalent of sleep. So the sleep API itself is not available because we don't have access to Windows API here, but ntdll execution is the one that's being called, in fact, by sleep. But now we can only call this directly. Whether this function is documented or not is something we can look up. Most of these functions are not documented, and that's intentional. Microsoft doesn't really want us to use this API. So they don't want anyone taking dependency on that. First, because the APIs, some of them are more powerful than normal Windows APIs. And secondly, Microsoft wants to have the flexibility to change things without anyone complaining. So the Windows API rarely changes, and if it is changing in some way, it's very well documented. But the native API, most of it is undocumented. Many of the documentation is actually available in the Windows driver kit because these are mirror functions. If you go back to the slides for a moment, let me see what I want to show you here. This slide right now is what that looks like when we call a function. So if you call a function from an application, could be a simple function like fread from the C runtime, or you might be using a different language like Python or C# or Java or whatever. You're calling their APIs. Eventually, they're going to call the read file function if they want to read from a file. And read file is going to call the native API, which is ntread file, which is part of ntdll. And then it's going to make the transition into the kernel. And the real ntread file function is going to be called. In fact, the ntread file function in the kernel has the same parameters as the ntread file function ntdll, which means that if I get a documentation for ntread file in the kernel, for example, in the Windows driver kit, then it's the same function. So it has the same semantics, the same meaning if I call it from ntdll. It's just that on the kernel side of things is the real implementation of ntread file that does whatever needs to be done, like call the appropriate driver, like ntfs, that does whatever needs to be done. So that is the idea. So if I know how to use these APIs, I can do things. And in fact, I'll show a few examples very soon of using these APIs. But in general, you can use these APIs in a normal application. You don't have to write a native application. And I'll show that in other examples here as well. I'm just saying that if you want to write a native application that can run, for example, at startup just like AutoCheck, then you can. You can do that by doing a few things, like removing all dependencies and changing your main to this function, which is the one that actually is expected by ntdll to actually be called. And of course, you lose certain things, like you can't have constructors for global objects running, but it's a small price to pay. And there are other ways you can go about it, and you have to kind of work slightly differently, but still you can do a lot of things using these powers. So AutoCheck is one of those examples. There's another example like CheckDisk. So in fact, CheckDisk is the equivalent of AutoCheck, but it is a Windows application. So I can call CheckDisk without any issues, just run it normally. So if I go ahead and try to run CheckDisk, I can do that. It will run. In this case, it requires me to run with admin privileges and all that. It will run. But if I try to run AutoCheck, here's what it's going to tell me. It's going to tell me that it's not going to run this because it can't be run in Win32 mode. Basically, it's saying that the create process API, the one that we typically use to launch executables, to create processes, cannot handle native applications. It just can't do that. And if we want to run native applications just like that, let's say for testing purposes, we can do that, but we have to write our own runner or our own creator, which I'll show you how to do. So I hope this makes some sense. Let's continue and see what else I can show you related to native applications and ntdll in general. So native applications are just the ones that have dependencies on ntdll only, but because of that little dependency, they have the ability to be part of boot execute and can be launched by SMSS when the system starts. So that's a nice thing that we get there. What else? If you look at ntdll, what is inside ntdll really? If we want to look at that, what would we find? So ntdll has a bunch of things. First, it has the image loader, which is responsible for loading other DLLs and doing some like mapping and binding to exported functions, things like that when we load DLLs. It has an implementation for the heap manager. The heap manager is about managing small memory allocations. So if you're familiar with memory allocations, there's the virtual APIs, which always work in chunks of pages. So it's like big allocations are good there, but what happens if you need to allocate, say, 20 bytes? If you use something like virtual alloc, you'll get a full 4K page, but you just need 20 bytes. If you try to allocate another 20 bytes, you get a different page. So the heap manager's purpose is to manage these small allocations in an efficient way. If you're familiar with a function like heap alloc, heap free, and all these kinds of APIs, these are using the heap manager, in fact. There's also some thread pool support in ntdll. The other things you'll find in ntdll are functions which look like the C runtime APIs, like memset, sprintf, things like that, which is kind of interesting. Why are they there? So first, let me show you that. If I go back to total PE and I go to ntdll, which I have here somewhere, and ntdll obviously has no dependencies, so it has no imports, it only has exports. And this is the native API. These are all the functions that belong to the native API. Most of them start with the letters NT. So if I do something like NT create file, I can search for that. Here's NT create file. That's the function I mentioned earlier. And if I look at the implementation by disassembling it, I really won't find like some gigantic implementation because it's not really here. The implementation is in the kernel. The user mode side just says, okay, let's put the number in EAX representing this system call. On my system is the value 55 hex, and then the syscall instruction is going to make the transition into the kernel to continue executing really NT create file. And so all the other native APIs that are really system calls are going to look like that. So if I look at something like NT create key, which is to create a registry key, you can see something which is basically identical. The only difference is that the number stored in EAX representing the system call number is different, but the rest of the code is the same, because really these are just like trampolines, just these jumps into the kernel, quantum leaps into the kernel. And so there's lots of APIs here, and one such section, you can see APIs like memcopy and memcompare and pow and memset, these kinds of APIs that you might be familiar with from the C runtime, because the C runtime also implements these APIs. These are part of the C standard, so they're here as well. So the question is why? I mean, we do have the Visual C runtime providing another implementation of these functions. Why do we have them in ntdll? And the reason is just to help those writing native applications. Because if I need to write a native application and I want to copy memory around, I want to use something like memcopy. It's a function that is easy to use, and it doesn't involve any kernel thing. It's just moving memory, copy memory from one location to another. There's no need to call the kernel for that. And so since I can't depend on the Visual C runtime, I can only depend on ntdll. It's nice that I get this support out of the box. Even for more complex functions like sprintf and strcmp and even qsort, the quicksort implementation, which is part of the C standard, I get that kind of for free in ntdll. So since native applications are mostly written by Microsoft, it's really to help Microsoft write native applications more easily, because these are just general things that are nice to have. So we have that in ntdll as well, just to make it easier to write native applications. But most of the stuff that is important in ntdll is related to those system call invokers, those NT functions that make the transition into the kernel, like NT create file that I've shown. And there are other functions there that start with the letters RTL for runtime library that provide higher level functions. Again, mostly they call NT functions eventually, or provide some nice feature like converting a string to integer and things like that. That again, if you would like to do that manually, it's a chore and it's a lot of work, and you want someone else do that for you if you only can depend on ntdll. So just to summarize that, you can see here some examples of how this transition to the kernel is actually happening within ntdll. I have here 3 variations. One of them is a 32-bit code from some Windows 8.1 system, and I have 64-bit code from Windows 10 or 11, and there's also ARM64 code for Windows 11 running on an ARM device, and so a CPU. And so you can see here that the ideas are the same. The only difference is in the number, the system call number. So for this particular system, the value here is 8A hex for NT read file. For the 64-bit version, the number is 6, and it's the same for ARM64. But the idea is the same. We put some number into a register representing the system call we would like to invoke on the kernel. And then the sysenter function, sorry, the sysenter instruction is the one used for 32-bit, syscall for 64-bit on Intel AMD processors, and SVC is the one used for ARM64. And again, it doesn't really matter if you've never seen assembly and that kind of scares you. You don't have to worry about that. It's just there behind the scenes. And so just every NT function is going to look exactly like that. The only difference is the change in numbers. And you can see the numbers don't have to be the same on different systems. In fact, these numbers change from time to time. It's not really predictable, and they're not supposed to be the same necessarily. But of course, on a certain system with a certain version, they will always be the same. But on a future Windows version, things could change. In fact, they do change. And in fact, there's a website, I don't exactly recall the name, but you can look it up, that has the list of all the system call numbers in all Windows versions, starting with Windows NT 3.1, the very first version. So someone did a lot of like crazy work there. And you can see that some of the numbers change, and of course, new native APIs are created, new system calls are created, so new numbers created, and sometimes system calls disappear. They also sometimes are removed from certain versions and so on. But most are pretty stable. In fact, the fundamental ones are pretty stable. So this is what that might look like. So we talked about that, and so every time you want to do something that makes that does really something real, like allocating memory, working with files, loading DLLs, creating threads, whatever you try to do, the kernel has to do that. In order to get to the kernel, you have to invoke system calls. And so you typically call a documented Windows API, but you don't have to. So technically, you can go directly to ntdll. The only thing that stops you, perhaps, is the fact that most of these APIs are not documented. That's one of the main reasons that I wrote the Windows Native API book that I already mentioned multiple times, because I try to document or provide information as to how to use these functions, because some of them are really useful and much more powerful than the normal Windows APIs. So now that we understand that, I want to show a few examples of this API, what we can do with that that we can't perhaps do with the normal Windows API. But first, I want to quickly kind of compare, if you're familiar with the normal Windows API, and compare that with the native API in terms of style and a few other aspects. So in terms of errors, if you're familiar with the Windows API, there's this get last error function you need to call to see what happens, because most Windows APIs return a Boolean that says success or fail, but if it fails, you want to know why, you have to call get last error. Some other cases, the error is returned directly. So there's no real consistency there. For example, registry APIs return errors directly, which is kind of annoying. The native API is much better organized, it's much better designed. Of course, the kernel APIs are the same. So they always return NT status, except for very few exceptions. And so you get the return value as the error value, which is NT status, just an integer, where 0 means success and negative values mean failure. In terms of strings, strings are typically used in the Windows API as a null-terminated strings, which is perhaps kind of easy because it's closely aligned with the C standard. But the native API uses Unicode string, which is a structure that describes a string. It describes a Unicode string, and it has a length there, something that does not apply to normal C-style strings. So they're always going to be converted to something like that before calling a native API. There's the create and open kind of functions. there's the specific APIs, and with native APIs, there's always a structure accompanying that called object attributes, where we specify things like names and some other attributes. So once you get used to the way the native API works and is designed, you get a hang of it, and then new functions you're learning about are very similar in the way you use them, which is nice. There's a lot of consistency there. It's less consistent in the Windows API. As we've seen, most of the APIs in native API start with NT or RTL. In the Windows API, it's a mess. API functions could have any name, and there's really no good way to know that one function is kind of related to another. Some of that is because of historical reason from 16-bit Windows and all that, but still, it's basically a mess. The API style in Windows API is very specific. For example, if you want to do something with the process, you have like gazillion APIs to do certain things with the process. With the native API, there's very few functions, like anti-query information process is a function that can give you process information, all sorts of information with a single API, just to specify the exact enumeration you want, what exactly the information you're looking for. And so it's a bit more generic. I wouldn't say it's necessarily easier, but at least you have less functions to deal with. Documentation, as I mentioned already, is full for Windows API. This is the official function Microsoft expects everyone to use. It's limited for the native API. Again, that's by design. But many of these functions are documented in the Windows driver kit because device driver writers need to use those functions as well. In terms of headers, Microsoft provides the official headers, but for the native API, there's a great resource called PHNT, the Process Hacker NT project, and it has almost full native APIs declaration. So just get it from GitHub, and I've done basically the same. So before I talk about some examples, I want to show a few more things related to native applications. So I've shown that I've written this simple native application. Let's say if I try to run it, and I mentioned already, we can't do that. So the question is, how can we actually do that? And the answer is we have to create our own runner. So what I've done here, created an application called native run, whose purpose is to run native applications. Basically, I have to use some native APIs like RTL create process parameters, and then RTL create user process to create process manually. So the details are something I'm not going to cover here, but the examples, of course, are going to be in GitHub, and I'll show the link at the end. And you can see how that is done. So with this, we can actually run native applications for testing purposes. So the basic idea is we create a process, and in fact, the first thread created there is suspended, so we actually need to call resume thread to kind of kick it into action. So let's see if we can do that. Let's see if I want to run this application. Here's native run my runner. I'm going to give it simple native as a parameter to run this thing. And what simple native does is just, as you can see here, it's probably maybe not easy to see, but it is using the sleep function to sleep for 10 seconds. That's what this is actually doing. Not very interesting perhaps, but good enough for demonstration purposes. The ntdraw text function here is not going to show anything on the screen because it only works as a native, as part of SMSS when it's running native applications at boot. So if you run this thing at boot, it will show you something. But here it's just going to sleep for 10 seconds. So I want to try to do that. Seems to be simple enough. I'm going to pass it to the parameter. As a parameter, you can see something is wrong. There is an an NT status returning there saying something is wrong. It's a negative value from a tools complement perspective, which means something is wrong here. It doesn't really work. And so we can try to figure out what that NT status is. In order to do that, I'm going to launch WinDebug. Just for fun, let's just launch WinDebug. Why not? WinDebug has a nice command called error that can do that for us. So let's just use that big thing just for this little purpose. I know it's a bit overkill, but still. So I'm launching a local kernel debugging session here, but it can be done in user mode as well, doesn't matter. I'm pasting this number, and it says, well, object path component was not a directory object. Something here is wrong with the path. Okay, so maybe I need to provide the full path because maybe there's no current directory. It makes sense. Let me just do that. So I'm going to give it the full path of the application I would like to run, the simple native thing. And I get the same error. I get the same error saying this path is bad. And if I check this, it doesn't really look bad. It looks good. It looks like exactly what I need. So what is going on here? And the problem is definitely not obvious. And that's because I'm using native APIs internally to find the executable. The native API doesn't really know what d: is directly. D: doesn't really mean a whole lot to the native API. Native API works with the native object manager namespace, which you can see in various tools. One of them is WinOBJ. So WinOBJ is a sysinternals tool. I have something similar, but here's a WinOBJ. And if you think about something like C:, D:, these things look like very fundamental things in Windows. In fact, they're not. If we go to this directory called two question marks, global two question marks, you can see D: here is in fact a symbolic link. It's a shortcut of sorts that points to this device hard disk volume 7, which is really what the function is expecting. It's expecting me to provide D: as device hard disk volume 7, because that's really what it is. So that's one way to change that. If I change D: to device hard disk volume 7, I can definitely do that. Let's try. Device hard disk volume 7, and I'll try to run this. Now it runs successfully. We have this process running. Here's a simple native. Here it is. It's running for 10 seconds because now it's been destroyed. So this works. In fact, when you use normal Windows APIs like create file and you provide C: something, what happens behind the scenes? The API has to somehow convert that to what this really is, because C: is, again, something like this. But there's an easier way to go about it, because we do have these two question marks as something we can use, because this is where these symbolic links are at. So technically, we can use these two question marks here. And it always starts with the root. So you can use some of these symbolic links starting from the root, and one of them is these question marks. So in fact, I can do the same thing by replacing D: with \, which is the root, two question marks, and then D:, something like this. And this should do exactly the same thing. You can see it succeeds and it creates the process. So in fact, when you call a create file function, for example, you provide C: something, what create file does, or ntcreate, before calling ntcreate file, it changes that to two question marks C: before calling ntcreate file. In fact, you can see that if you do some user mode debugging, and if you're familiar with WinDebug, you can definitely see that in action. I don't really have time to show that, but it is what is happening behind the scenes. Because the native API, just like the kernel, always looks from the root of the object manager namespace, from this. That's what it sees. It doesn't see what C: is directly, but it is close enough because of that two question marks, which is a directory in the object manager namespace. These directories, by the way, are not in any file system. These are logical directories. They're all in memory, just representing some hierarchy. And there's lots of other interesting stuff here, but that's beyond the scope of this talk. Okay, so hopefully now we have a better understanding of what is going on in terms of native API and getting some feel to what it is. Let me show you and discuss a few examples of what we can do with that API. So first, if you look at system information, there's this gigantic function called ntquery system information. And just like I mentioned, this is a very generic function. So the thing you actually want depends on the system information class you provide. And there's a long list of information classes. You can see here just a partial list of the enumeration there. You can see there are more than 200 items you can ask for. And for each and every new Windows version, there's typically one or two more that are added to this list. You can get lots of information there without having to work very hard. So what am I talking about? What kind of information? For example, processes. Let's say I want to enumerate all processes in the system. If you look at tools like Task Manager, and Process Explorer. They enumerate all processes in the system, obviously. How do they do that? Well, the Windows API has some documented APIs to do that, like create tool helper, snapshot, you have WTS enumerate processes, you have enum processes, and these APIs are useful, but they're limited. The information they provide is limited. You get just a few details about the process. If you want to have more details about the process, your only choice using the normal Windows API is to call the open process function, get a handle, and then call some function that gives you more information. Now, the problem with that, first, it's slow. It requires you to have another call to open the handle to the process. And secondly, some process you just can't open necessarily depending on your powers. So open process might just fail, and you can't get those extra details that you might want. And so instead of that, you can use the NT-query system information function with the system process information. One of the enumeration values is also an extended one, and you get lots of details for free without having to open any handles. You also get thread information for all the threads in these processes if you want it. It's part of that information. Here's an example of what you get. You get this gigantic structure about a single process. So it's not just the process name and the number of threads or creation time. You get lots and lots of details for free with a single API call. In fact, this is the API used by Task Manager and Process Explorer to get the information that they provide, because it's much faster. And in fact, some of the details here, there is no API to give you that. And so you get all this stuff for free. You don't have to be an administrator even. If you are an administrator, you can get even more information by this extended process information structure. You need even more stuff. So that's one thing you'll find in native API. You can get more information with less calls, and sometimes things that you can never get. For example, the process sequence number here, it's a number that always goes up. It's not like a process ID which can be reused, but instead this number always goes up and never goes down. So it provides a unique way to identify a process on the system. You don't have to have the process ID and the creation time and all that. So this information, for instance, cannot be retrieved by normal Windows APIs. There's just no API that provides that. Another example, we know that if you look at something like Process Explorer, with Process Explorer, we can look at the information here at the bottom, and we can see a list of handles in a particular process. So the question is, how do we get this list of handles? If you look at the Windows APIs, there's just no such API. You cannot enumerate handles in your process or any other process for that matter. But the native API provides that information using the same NT-query system information API. You can get all the handles of all the kernel objects in the system, which is exactly what Process Explorer does. And so in general, kernel objects, we know that these are data structure in kernel space, and in user mode, the only way to get to them is by using handles, which are private to the process, just these little numbers. And sometimes it's useful to see what every process has, or a particular process has, in terms of handles. And so NT-query system information with system handle information allows you to do that. You get a list of all the handles in all processes, including protected processes. It's kind of nice. Maybe it's a bit too much. Maybe it shouldn't really work like that. Maybe it's divulging some information which we shouldn't really be divulging if we're writing the kernel, but it is what it is. It provides all the handles in the system, including handles within protected processes. And that's a very powerful thing to do, to have. So here's a little example. So here's an application called Media Player. I like to show this example because it's kind of funny. So the Media Player application is something that that's the old Media Player, the legacy it's called now. Okay, fine. So if I run it, it runs. It looks nice. Let's say I want to run another Media Player. So if I go ahead and try to run another Media Player here, I try to run another one, you can see it doesn't really work. It seems not to work. I just get redirected to the existing Media Player. So what happens here behind the scenes that in fact it is launching another Media Player, but somehow the Media Player knows that it's not the first one and just gives control to the other one. And the question is, can I change that? Can I still use my, I want to launch more than one Media Player? Seems reasonable enough. So in fact, we can do that. If we do a little digging, we'll find that this media player has a way to know that it's actually has another instance running by using a mutex, a named object of type mutex in this case, that has a very specific name. So let me find that, and that mutex has this name. It's called Microsoft WMP70 check for other instance mutex. Kind of a big hint as to what the purpose of this mutex is. So basically what happens, the second media player looks for a mutex with this name. If it finds it, it just says, I'm not the first, let me just find my other media player and send it a message. Instead, I can do here, I can right click and close a handle. So normally closing a handle behind the process back is a bad idea. In any case, how do we actually do that? But if I do that anyway, it becomes red and goes away. So here goes, it's dead. And now if I go ahead and try to launch another media player, here goes, it works. Here's another media player. Now I have two media players. And I can do the same trick now and have any number of media players that I want. So what happens if I want to do the same thing, but programmatically? I want to do it myself automatically. So I've done that. So I can have WM player. How did I call that application? It's called invoke WM player. Okay. So if I do invoke WM player, I get one media player. If I invoke another media player, which is the tricky part, I can get another media player, which means I'm doing that closing of the handle automatically by running some code. Notice the first instance says that there's no media player alive, but the second one located the media player but managed to launch another one. And so to do that, I have to search for the handle and close it behind the process back. So the way to do that is first to search for the handle. So this is what I've done here in this example. Let's see. So the first thing that I'm doing is to look for, well, one of the things that I'm doing is looking for handles. So I have here the ability to ask for the handle table of a process. And when I get that, I'm looking for that particular name. And if I find it, I'm closing it. And you might be thinking, how can I close a handle in a different process? I mean, if I call the close handle API or the anti-close native API, which is its equivalent, I can only close the handle in my process. So how can I close a handle in a different process? Apparently, this is something we actually can do. It is, in fact, supported by the duplicate handle API. If you use this particular constant, it's closing the source handle. So technically, can duplicate that into my process and then close it as well. And the handle is gone. And the object itself is also gone because it only had that one single handle holding it alive. So I'm doing all that automatically. Again, I'm not going to cover the entire code, but you can see that later on if you're interested. So these kinds of things I can only do with the native API. I can't do that with the normal Windows API because there's no way to get that kind of enumeration. So that's one nice thing. Now, some people have a trick that allows them to open objects that might be in a different object manager namespace directory by using this idea of using global root, which points to two question marks, so to speak, and then maybe I want to open known DLLs. If I go to WinOBJ, there's this kernel object and there's known DLLs. This is just a directory in the object manager namespace. It has a bunch of sections. I'm not going to talk about what that actually does, but it's there. So let's say I want to open a handle to this section. The section is memory mapped file. That's the terminology used in the Windows API. Let's say I want to open a handle to that. So if I try to do that using the Windows API open file mapping, which is what we would do in a normal kind of case, it doesn't work. We get something saying bad path name. It's not really supported. But if you use the native API anti-open section, it works just fine. We just provide the normal path as we see that from WinOBJ, from the root / directory down to the actual object we want, which in this case is called kernel-base.dll. Notice kernel base is here. It's a section object, just has the name that looks like a file, but in fact it's a section object. So we just point the path to it, and the native API is able to open that. So native API allows us to open things that the normal Windows API would not allow us to open. Again, something which is more powerful. What else? There are some specialized things that native API supports which you don't get with the normal Windows API. For example, we can suspend the process in a single call to anti-suspend process. There's no equivalent for that in the Windows API. What does it actually mean to suspend the process? It means suspending all the threads in the process. So we could potentially do that with the Windows API by somehow enumerating all the threads in the process, suspending each one of them. Is it possible to do? Yes, it's possible. But it takes more time because it's not being done in one stroke in the kernel. And we can also miss threads. While we're enumerating, another thread might be created and then we're actually not suspending everything. So anti-suspend process takes care of all of that and doesn't allow new threads to be created just while we're suspending the process. So it's much more powerful. In fact, Process Explorer uses that. If you go to Process Explorer and right-click some process and say suspend, that's exactly what it's doing. It's calling anti-suspend process. And of course, we have the opposite function to resume a process. And other things we can do is to go to the process environment block in a different for any process we want to find where the PEB is and then manipulate it. For example, with Process Explorer, we can double-click any process and we can see its environment variables here. How does that really work? Environment variables are on per process basis. In fact, they are stored in the PEB. So how can we get to that? We have to read the process memory somehow and get to the PEB. This is exactly what Process Explorer is doing. And now we can do it ourselves. In fact, I've done that in one of the other examples here, where I'm reading an set of environment variables from a different process. And the basic idea is to open the process, find the location of the process environment block in this structure called process basic information. And then from there, I can use nt-read virtual memory, or if you will, read process memory to read information from the other process properly and parse that environment block. That's exactly what Process Explorer is doing. I couldn't do that if I didn't know where the PEB of that other process is. But I can get that information very easily just by calling this function nt-current-information-process with process basic information. So native API, again, saves me if I want to do these kinds of things. Okay, what else? Another thing we can get with the native API is the ability to register for DLL load and unload notifications. If I say inject some code into a process and want to know when DLLs get created, they get loaded and unloaded, I can get those notifications. There's no Windows API that provides you that capability. You can only get that with a native API. Same ideas with memory. Although most of the things in memory, we can use the normal Windows APIs like virtual alloc or virtual alloc EX. We don't have to use the native APIs, but there are some niceties there as well, like RTL query heap information that allows you to query information about the heap in a different process. There is no equivalent to that in the Windows API. This is what tools such as VMMap that is using. If you're familiar with VMMap from sysinternals, it's doing that to get information about heaps in other processes. This is a pretty complex function that injects code into the other process and things like that. So it's nice that we get that kind of out of the box if you use the native API. And there are more stuff in the native API like ALPC, which is the internal communication mechanism used by Windows components, more stuff related to I/O, jobs, security, threading, registry, or more things related to the loader. Lots of stuff in the native API. In my book, I try to cover a lot of that, but obviously not close to everything because there's just a lot of stuff there. I try to cover the most interesting things perhaps, but maybe someday I'll write a second edition with more stuff from there, because it does require research and trying things out and reverse engineering and these kinds of things, which is not necessarily easy. And of course, you have to take these things with some degree of skepticism, because things could change. Microsoft is not obliged to keep the native API behaving in the same way going forward in different Windows versions. That's part of the kind of risk, I would say. But in practice, most of the APIs are pretty stable because Microsoft has their own tools that use that, like Task Manager and Process Explorer. And so changes are really pretty rare, but they do happen. So no guarantees there. It's really about trying to use the most powerful API from user mode that we can. This is still all user mode, and I have to stress here that with the native API, you don't get any special kernel powers. It's not like that. You're not in the kernel. You're still invoking all these things from user mode, but you do have more flexibility in APIs, and you can get more information for certain APIs, as we've seen. If you are running as a native application at boot, as I described, then you do have like lots of powers there. You are running with a system account and have all the privileges available to you. You can do lots of things at that point in time. But of course, to register that, you have to be an administrator because the boot execute value is under HKey local machine. So this is kind of a whirlwind tour of the native API and giving you a sense of what that does. Yeah, that's it for me for this session. Thank you.
Thank you so much for your very engaging presentation. It was really a pleasure to listen to you.
Thank you.
And right now, slowly from US, we are moving to United Kingdom. Because next our speaker will be Rol Jafari.